In the next unit, we're going to be looking at organic acid-base reactions. And so I want to take a look at a couple of organic acids before we do, just to see how resonance is going to play a role in stabilizing their conjugate bases. So right now I'm drawing a carboxylic acid. And a carboxylic acid is a carbon-containing compound where we then have a carbon that is double bonded to an oxygen, single bonded to a second oxygen, which then has a hydrogen attached. And it is this hydrogen that can be easily lost for this to act as an acid. So a common acid-base reaction would be for this to react with ammonia or with some sort of an amine. And so I'm going to go ahead and show it reacting with propylamine, which is a 3-carbon chain with a nitrogen attached with 2 hydrogens. And of course that nitrogen has a lone pair. Now I didn't include them here, but I'll go back and put in for right now our lone pairs on the oxygens. And because I'm going to show the mechanism for the nitrogen removing this hydrogen, I'm going to use my green arrow. It's more of a teal arrow, and I still have it in translucent mode. So let me go over that again, make it a little bit darker for you to see. There we go. This lone pair, we sometimes say attacks the hydrogen, but that really just means that it's going to share its electrons with the hydrogen and make a new bond to that hydrogen, which is going to result in the electrons in the oxygen-hydrogen bond being pushed back onto that oxygen. And when those electrons are pushed back onto that oxygen, what we get in this chemical reaction is the formation of what we usually refer to as the carboxylate anion, or just the carboxylate ion, with a formal negative charge on this oxygen. There we go. And then, of course, we're also forming the protonated amine in this process. So I'm going to just change colors there. And so the amine that we form here would have now 3 hydrogens attached to the nitrogen, so there'd be no lone pair, which means now this nitrogen has a formal positive charge. Now, this has no good resonance structures. This nitrogen is actually now tetrahedral, with having both a carbon and 3 hydrogens attached to it. But this oxygen down here, that's bearing this full formal positive charge, can actually share this negative charge with the other oxygen over here. And it's a pretty easy resonance process to see. Let's imagine we've got this lone pair here, now being shared in a carbon-oxygen double bond, which would then require us to push these electrons out here. And our resonance structure here, excuse me, we'll now have the double bond here. Oxygen still has 2 lone pairs, but the other oxygen now has 3, which then means it has the full formal negative charge. Now, if we wanted to think about the resonance hybrid for these 2 structures, remember, neither one of these is really the correct structure. It's only the combination of these 2 structures that really does a good job of representing the distribution of the negative charge in this compound. That is to say, the distribution of electrons. But you'll notice sometimes when we draw our resonance hybrids, I do leave off the lone pairs, and that's because there's not really a good way to show, half lone pair density on 2 oxygens. But it is pretty easy to imagine the fact that we have partial bonds here by just using kind of a dotted line. Now, instead of showing the partial negative charge on both of these oxygens, which we sometimes do, you'll sometimes see something like this with a negative charge shown just out adjacent to, indicating that the electrons are being spread out through this region. That's fine. I kind of like the partial negative on both of the oxygens only because that does a better job of representing where those electrons actually, that electron density really is centered. So let me just erase that here, and then I'm going to go back and put the partial negative charge on each of those oxygens. And let's look at one more example of the conjugate base of an organic acid. And in this case, we're going to look at the acid phenol. This is a pretty important acid. Phenol is actually just a benzene ring with an OH or alcohol group attached. And just like in our previous example, a base can come up and remove this hydrogen. Now, it turns out that amines, while they can partially deprotonate a phenol, the difference in the acidity and basicity of the compounds and their conjugates is not so great that it would completely ionize it. So instead, what I'm going to use is just hydroxide to show the deprotonation of this. And so let's imagine we've got the OH minus ion. The OH minus ion, of course, has a formal negative charge. And it's going to come in and remove this hydrogen, which we might say it's attacking that hydrogen. Just because we are being careful with our arrows right now, and we should really always be careful with our arrows, but I want to be very, very clear that this arrow is coming from this lone pair here. I have not really done a very good job. So let's try one more time. Let's see what we can do. There we go. So I want to show that the electrons are coming from this lone pair here and are making a bond to this hydrogen. That is much better. And then, because we're making a bond to that hydrogen leaves its electrons behind on this oxygen. Now, I didn't show the other lone pair here, and that's fine. But once I get to my product, and I'm going to go down this way now just to give myself a little more room. Since this oxygen is now going to have a formal negative charge, it's probably a good idea to go ahead and show all 3 lone pairs, just because it kind of helps you keep track of what that formal charge should be. There we go. Now, of course, in this process, I'm also making a water molecule. So sometimes we'll show when a molecule isn't one that we're particularly interested in, but that it's produced in the process. We might show an arrow coming off, and then there's the water molecule, of course, formed from the OH minus and the H plus that was removed here. Now, this phenolate anion is more stable than most alcohol anions or alkoxide anions because the electrons on this oxygen here can be delocalized throughout this pi system here of the benzene ring. So let's go ahead and look at those resonance structures. So I'm going to move these electrons to make a double bond between the oxygen and carbon here, but that means then that the electrons here are going to get pushed out onto this carbon here. And so as we start thinking about our next resonance structure, we're still going to have the benzene ring. Now, instead of having a single bond to this oxygen, I didn't do a great job with that ring, so let's go ahead and make that again. There we go. But now we have a double bond to this oxygen, and this oxygen would still have, or would now have 2 lone pairs instead of 3. It also no longer has a formal charge because now it's using that extra lone pair to make the double bond here. But because we pushed an extra pair of electrons out onto this carbon here is going to have a negative charge, and I'll come back and put that on in red, just to highlight it in a second. But these 2 double bonds are still in the same place, so let me go ahead and put that double bond there and that double bond there. And then what we're going to do is look at how this negative charge can continue to be pushed around the ring. Now, it can't go to every carbon in the ring, but it can go to the one that we would say is ortho to this substituent group, the one that is para to the substituent group, and then the other ortho position. Where we'll see that it cannot go is to the 2 meta positions. So we'll move these electrons here. And when we move that pair of electrons back to form a double bond here, then again, we're going to have to move this double bond somewhere else. This pi bond then will be converted into a lone pair of electrons on what we call the para carbon, the one across from the carbon-oxygen bond. So we still have the carbon-oxygen double bond there. We still have this double bond here. We've introduced a double bond there, and now this carbon has the lone pair of electrons, and then that means it also has the formal negative charge. Now, it's really important to always show formal charges in your electron dot structures. And so that means if you have multiple resonance structures, you do need to show that formal charge in each resonance structure. Now, let's show moving these electrons out onto this position. So to do that, I'll push those electrons here into a pi bond. That causes this pi bond to push its electrons there. And so what's going to turn out to be our 4th and final resonance structure has our double bond here. This has moved into a double bond there. Of course, we still have the double bond over here. And now our lone pair is here. Now, I did say that this was our 4th and final, but technically that's not correct. If you think about what would happen if we move these electrons here and push those electrons back out there, we wouldn't have exactly this structure over here, but it would be very, very similar. The only difference is that all the double bonds would be shifted one over. So technically speaking, that is our 5th resonance structure. Sometimes we don't show that 5th resonance structure because pretty much any time you see a benzene ring like this, the alternate version where you just move them over is pretty much understood. Since we're talking about it, I will go ahead and make that final electron push of putting those electrons there, pushing them out there, and then giving us what is truly our 5th and final resonance structure. So now we have a double bond here, here, and here. We're back to a single bond on the oxygen, back to 3 lone pairs on the oxygen, and therefore back to a formal negative charge on the oxygen. And so let me go ahead and draw in my brackets. Those are not very good brackets, but I think you get the idea. The brackets, of course, should look a little bit more like this. But we usually put our resonance structures together in a set of brackets to really kind of indicate that these are really all part of the same structure. It's not 5 different structures. It's 5 representations of the same structure that are required to get a really good understanding of the distribution of charge within the molecule and the distribution and the bonding patterns of the electrons. If you wanted to draw a resonance hybrid here, we'd probably just show kind of our standard benzene resonance, and then show this kind of entering into that benzene resonance to just illustrate the fact that the electrons are being spread out between this oxygen and the various carbons. We'd also probably show in our resonance hybrid a partial negative charge on the oxygen and partial negative charges on the 3 carbons that have formal charges in the 3 resonance structures where we've put formal charge on carbon. Now, sometimes when we do this, we might even try to differentiate the fact that carbon having a negative charge isn't as good as oxygen having a negative charge because, of course, oxygen is more electronegative. And so what we might do here is show this as having kind of a double negative, meaning a double partial negative. It looks like I've drawn some glasses here. So let me, once again, kind of separate this off. It's the lowercase delta, and then what I've done is shown that it has 2 negative charges. I don't know that my new drawing is any easier to discern than my other one, but it is, once again, that lowercase delta and showing the slightly more significant negative charge on the oxygen versus the carbons. And that's probably that set of 3 examples from the previous video and this one is a pretty good representation of the different kinds of resonance structures that we're going to encounter over the course of the semester. Of course, there's going to be a number of practice problems and some problems on the problem sets and on quizzes or exams that might require you to show some resonance structures. So be sure that you get plenty of practice with those.